Greetings, everybody. Learning is a hobby here. I want to finally get around to experiment three in Charles Platt's Make Electronics. If you haven't seen my first three videos, actually, you should check those out before you look at this one because the experiments build on each other. So there's my first video is introducing the book and the project kit from Protect Trader that I'm using to do the experiments. And then the next video is project one. The one after that is project two, and then we're going to do project three. Sorry, no, sorry. We did project one, two, and three. Now we're going to do project four. Sorry. So check out those videos if you haven't seen those yet. So in experiment four, let me read the sort of intro that Mr. Platt has here. Electricity can generate heat. You know this must be true because there are electric water heaters, electric stoves, and electric hair dryers. Also, when the 9-volt battery burned out the LED, perhaps that was because the LED became too hot. If you again, this is why you should look at the previous videos. In one of the experiments, we burnt out a red LED. So perhaps it's because the LED became too hot. Perhaps. Once again, I have to nail this down with numbers. And then the supplies that we need for this one are a 9-volt battery, which I have here, which comes in the kit from Protect Trader. I need a 15 ohm resistor, and I have the pack of 15 ohm resistors here. I need a cartridge fuse 5 millimeter diameter, rated 1A. That is this one here. So we get one of those in the project kit. Um, we need a cartridge fuse 5 millimeter diameter, rated 3A. That's this one. Again, both of these come in the Protect Trader kit. Then I need two test leads, one red, one black. I have those here. And then I need my multimeter, which I have over here. Okay, so let's start the experiment. So the next part in the book is titled "Overheating a Resistor." Okay, so Platt says connect the 15 ohm resistor with your battery as shown in Figure 4.1, but don't try it for long. You'll find that the resistor gets hot quickly. Let me just show you the diagram real quick. So we want to hook up the 15 ohm resistor to the battery like this. Okay, so I've set up the system here, and we want to connect these, and he says, whoops, not to do it for too long because it'll get hot. It's kind of hard. I guess you can't really see heat, so I don't know how I would see that without touching it or anything. Okay, well, oh, actually, I do. It is hot. Okay, so that's the first thing that he wanted us to do. Let me detach this just so it doesn't exit. Ooh, wow, that really does get hot. Uh, I just detach it so I don't accidentally connect the pieces together again. Okay, let's see what the next thing is. Just want to check okay, the audio is still going. Important note, don't try this with a bigger battery. Definitely don't try it with lithium batteries that provide power for laptop computers, power tools, phones, and other portable devices. Lithium batteries can behave badly, as in Figure 4.2. He has a picture here of a lithium battery exploding. So it's also a bad idea to mess around with lead acid batteries. Bear in mind that a car battery can deliver enough current to weld two pieces of metal together. Anyone who has ever dropped a wrench across the terminals of a car battery will know this, assuming they survived the experience. This is why a car battery is solid with a plastic cap over the positive terminal. See Figure 4.3. He has a picture of a guy electrocuting himself with a wrench over here. Um, Now that you've established that electrons traveling through a resistance do create heat, I want to calculate how much. This will require working in watts. P.S. Don't forget to disconnect the 15 ohm resistor. I already did that. So Okay, so the next section says temperature, heat, and power. Temperature is an attribute of an object, like its size or its weight. Heat is a transfer of thermal energy from one place to another. This can be done by conduction, convection, or radiation, and is measured in joules, abbreviated with a capital J. If you get hot by sitting in front of a campfire, joules of heat energy have been transferred to you from the fire because its temperature is higher than yours. Power is defined as the rate at which heat is transferred and measured in watts. 1 watt is equivalent to 1 joule per second. Watts can be defined differently when dealing with electricity, and there's an equation here: watts equals volts times amps. Uh, so amps, remember from previous sections, represents it is the unit that we measure current in, and volts is the measure of the voltage drop across a resistor, for example. However, letter P is often used to represent power. So you may see this formula: P equals V times I. So watts, again, watts equals volts times amps, or power equals voltage times current. And we've seen some other equations in the previous experiments as well, if you recall. When your 15 ohm resistor got hot, you could feel it with your finger. And believe me, actually, it took a second, but yeah, it got really hot. So really, you were feeling the transfer of heat into your finger, and the faster it happened, the more painful it would be. Also, the more quickly electricity generates heat inside a component, the less chance the component has to get rid of the heat in the world around it. Therefore, the rate of heat transfer is more important, and watts are the unit we use to express it. And then he has watt conversions here, the unit conversions, but they're the same prefixes that we've seen before, so I won't belabor that. The origins of wattage. James Watt, shown in Figure 4.5. I'll show you the picture in the camera here. That's Mr. James Watt. Born in 1736. Oh, sorry. He's known as the inventor of the steam engine. Born in 1736 in Scotland, he set up a small workshop in the University of Glasgow where he struggled to perfect an efficient design for using steam to move a piston in a cylinder. Financial problems and the primitive state of the art of metalworking delayed practical applications until 1776. James Watt's development of steam power enabled the Industrial Revolution, and despite difficulties in obtaining patents, which could only be granted by an act of parliament in those times, he and his business partners eventually made a lot of money from his innovations. Although he predated the pioneers in electricity, his name was not assigned to the basic unit of power until 1889, 70 years after his death. Okay, while your tongue did not get hot. So this was experiment one. Again, if you haven't seen that video, you should go back to the my video for experiment one. Now you know what's what. Ha ha ha. You can calculate heat transfer very easily. Maybe you thought that when you touched the battery to your tongue didn't get hot, but actually it did, just a tiny bit. How tiny is tiny? Because watts equals volts times amps, we have to begin by figuring out how many amps flowed through your tongue. I will use Ohm's law for that. You can check the back, you can check back in your notebook to find what you actually measured, but let's suppose your tongue had a resistance of 50,000 ohms when you applied 9 volts across it. You don't know the current, but you want to know it. So you use the version of Ohm's law, I equals V over R. That's a formulation of Ohm's law. It's usually written V equals I times R, but again, you could divide by R, which represents the resistance measured in ohms. All right, and therefore I is 9 divided by 50,000, which is 0.0001 amps. Um, I won't do the calculation for my own tongue because I didn't actually do that experiment. Again, look back at my video on it, and you'll see why. But so these numbers Charles Platt got from doing the experiment himself. So that's how many amps, approximately, traveled through his tongue when he put the battery across his tongue. Now you can find watts by multiplying the voltage difference by the current. So W again is V times I. So W is 9 times 0.00018, which is 0.00162 watts. What would that be in milliwatts? Move the decimal point 3 places to the right, and the answer is 1.62 milliwatts. That's a tiny amount. The high resistance of your tongue limited the number of electrons per second, which limited the amount of heat they could generate. So you didn't feel a thing apart from a tingle, which was just your nerves being stimulated by electricity. Okay, why did the resistor get hot? The resistors that you have been using are rated to deal with a maximum of 1/4 watt. You can buy resistors that handle more power, but for the rest of the projects in this book, it isn't necessary. I wonder, did the last experiment with the 15 ohm resistor push it a little too far? Once again, start by using Ohm's law to calculate the current. You put a 15 ohm resistor across a 9-volt battery. So again, I is V over R. That's again Ohm's law. Therefore, I is 9 over 15 or zero point 0.6 amps. Now that you know the current, you can calculate the watts. So W equals V times I, or power is voltage times current. So 9 times zero point 0.6 is 5.4 watts. Yikes, 1/4 watt is 0.25 watts. So you were applying more than 20 times as much power to the resistor as it was designed to handle. This is why I told you not to connect it for very long. No wonder it got hot. Okay, and then we're going to do some experiments with these fuses now. So the next section is titled Use a Fuse. The formulas that I provided are wonderfully simple, but they have their limits. Suppose you put a straight piece of wire across a terminal of a 9-volt battery, and the wire has a tiny resistance, maybe 0.01 ohms. In theory, Ohm's law says that the battery will push 900 amps through it, and when you multiply that by 9 volts, the power will be 8,100 watts. This is almost enough to power a whole house. Can you disconnect your home from the grid and just wire a 9-volt battery into your breaker box? Probably not. There's a limit to how much current a battery can deliver because the chemical reactions inside it, which generate electricity, can't occur fast enough. Ohm's law only works when your source of current is stable. So how much power can you get from a 9-volt battery? You can simply set your meter to measure amps and hook it up to the battery, but that might not be good for your meter. I have a different plan. You can use a fuse. I included a picture of a fuse back in figure 112. Check it if you need to refresh your memory. That's okay. I have the fuses here. You know, Protect Trader. The Protect Trader kit comes with the fuses labeled here. So, okay. So where did I leave off? This is a cartridge fuse consisting of a tiny glass cylinder with a metal cap at each end, and a thin wire that runs down the middle. Uh, at each end, and a thin wire that runs down the middle. The wire is made of a special alloy that melts very easily when too much current runs through it. The purpose of a fuse is to protect other components in a circuit by burning out before they have a chance to burn out. This is known as blowing a fuse. The fuses you'll be using should be 5 millimeters in diameter so that you can grab them with your test leads. Alternatively, you can use automotive fuses that have little tabs sticking out. One fuse should be rated 1A, while the other is rated 3A. I have both of them here. They appear identical, but if you look very closely with a magnifying glass, one of the end caps of each fuse will have 1A or 3A engraved in the metal, probably with a couple other numerals and letters too. After you check the fuses, don't get them mixed up. Maybe put a different colored dot on the end of each one using a marker pen. A fuse has no polarity. You can use it either way around. Okay, so start with the 1 amp fuse, attach it to the battery as in figure 4.6. Let me just show you that. All right, this one here is figure 4.6. Press the loose alligator clip against the fuse for only 2 seconds. That should be enough to melt it. Don't worry about the fuse getting hot. The elements inside the fuse will melt very quickly before you can feel the heat outside the fuse. The schematic version of figure 4.6 is shown in figure 4.7. It's right underneath the picture that I just showed. Why are there so many? Sorry. The schematic is in figure 4.6. Figure 4.7, which shows a variety of symbols that are used to represent a fuse. I should probably show you those. So these are different symbols that are used to represent a fuse in a schematic. Uh, Why are there so many? I really don't know. There are even more that I didn't show here. I just chose the ones that seem the most common. Remove the fuse from the circuit and take a close look. Don't peer closely at a fuse which still has current running through it. That's a bad habit. If a fuse is heavily overloaded, it can blow up more dramatically. Um, do, let's see. Should I just do it before I continue reading? Maybe I should. Let's take out the one. The I think he said the 1A fuse. Just double check. Start with the 1 amp fuse. Yeah. Okay. So here in the Protect, I should just show you in the Protect Trader kit, the fuses come labeled. So this is the 1 amp fuse, and there should be. If I open this up, I probably won't be. It probably won't show up on the camera, but there should be a label of 1A on one side here. Uh, there might be, but I. Oh, I see. It's on the actual. Yeah, this isn't going to show up on on the camera. I'll bring it there. Maybe you can see that there's a marking there. Okay, so we want to blow this fuse. Now, don't think this is gonna be easy to see on the camera, but we'll do it. All right. So he says it doesn't matter which end it goes where. So I'll clip the positive end here, and the negative end. I'll just tap it here, and maybe if I put this by the white paper here, maybe I'll be able to see the. Yep. So it's a very tiny wire, and I don't know if this will show up. You probably won't be able to see it on the camera because the wire is so tiny, but the wire split in the middle. Okay, so we just blew our 1A fuse. So I'll put that on the side here. And let's see what Mr. Platt will do next. All right. Do you see a break in the element? It should look like figure 4.8. And I can barely see it because the wire is so tiny. Like I said, I don't think it's big enough that the camera will be able to focus on it, unfortunately. It should look like figure 4.8. If you don't see a break, repeat the experiment for 3 seconds. Fuses are not accurately rated. Some 1 amp fuses may require more current to melt than others. Because you melted the 1 amp fuse, you can feel sure that more than 1 amp flowed through it, assuming it was accurately rated. But how much more? Let's try the 3 amp fuse. Repeat the experiment, and this time leave the fuse connected for 4 seconds. Remove the fuse and check it. I'm hoping and expecting that the fuse didn't melt. It didn't, did it? Well, let's actually see if if it does or not, and then we'll take a look at what he says next. All right, I should probably show this. This is the 3 amp fuse, by the way. Okay, so I'll hook up the battery again. Maybe I'll just touch the clips together. Okay. So I did that for a few seconds, and I don't know again if you'll be able to see this, but I put my hand here. Why the wire is still intact. Yeah, it's probably too thin for it to show up on the camera, unfortunately, but you'll just have to trust me that it is. All right, let's see what he says next. Okay, so now you know that the current is more than 1 amp and less than 3 amps, assuming the fuses are accurately rated. Even if they're not accurately rated, the 3 amp fuse surely must melt more easily than a 10 amp fuse. Therefore, it would be safe to measure current with your meter, so long as you use the socket labeled 10A or 20A. There's a, if you've seen the previous videos, there's a socket on the multimeter. Let's see, it's measure. Sorry, it's labeled. I think I have 1A and 10A. It's kind of hard for me to see in this light, but it's on there. Sorry, 10A and 20A socket. Typically, they can deal with the maximum current for maybe 15 seconds, after which they need a half-hour cooling off period. After this experiment, move your red meter lead back to the volts ohm socket. Now you can connect the meter directly to the battery to measure its voltage, as you did back in 313. Okay, so he wants us to measure the voltage across the battery. All right, let me actually do that now. And hopefully I can read the. Okay, I'm gonna put this to 20 volts here, DC. Let's see, and I have this is in the volts ohm socket. Okay, and then I can measure the voltage. Let me see if I can put this so that the measurement will show up on the camera. Okay. You know what? Let me do it like this. It's the leads tend to want to slip off. So maybe if I do it with the alligator clips, it'll be easier to do this. All right, so that's the reading. So it looks like 9.29. So actually, it's still pretty good, the battery. Okay, so let's see. My battery voltage was 8.73. In your notebook, you should have accumulated a whole series of measurements so you can see the effect that the experiments had on battery voltage. I haven't actually written it down, but I have everything recorded in the videos. So batteries don't last very long and they are loaded beyond their limit for which they are designed. Okay, the next section is labeled current conclusions. What can you conclude from this experiment? And there's 2 bullet points here. Even a little 9-volt battery can deliver more than 1 amp. In theory, that's enough to light 50 LEDs if they were wired in parallel. And then bullet point 2, but a few seconds delivering this current will deplete the battery. How much current should the battery have delivered through the fuse, according to Ohm's law? Well, that depends on the resistance in the circuit. You may think that resistance of a meter and a fuse is next to nothing, but actually the fuse has more resistance than a piece of ordinary wire. You can take it out of your circuit and measure it with your meter. My fuse has a resistance of zero point 0.5 ohms. So let's actually do that real quick. We want the three amp fuse. I should have left the alligator clips attached. I didn't realize that we were going to be doing another measurement. So, but it's quick. Let's do this. Put this in on resistance. Let's see. I want 200 ohms, maybe. Oh, I should show this to you as well. Uh, Hang on. Where's my attachments here? Let me look at. Hang on 1 second. Okay, so this has to go here, and then I can touch this here, and let me just make sure that this shows up on the screen. Oop. Okay, that I didn't mean to do that, but sorry, let me just pause this for 1 second and find where that went. Okay, sorry about that. It took me a while to find find the fuse. And also I should sorry, I should have let me clarify something. I shouldn't have hooked the battery up. Sorry, to test the resistance of the fuse, all you have to do is plug it through the multimeter, and I have it set to 200 ohms. And if I connect, I don't know why it's not so. It looks like maybe it's between 2 and 3 ohms, I guess. Let me see what Charles Platt says. Okay. He said my fuse has a resistance of zero point 0.5 ohms. I hope I didn't destroy the multimeter by plugging things in the wrong way. Um, All right, now what about the meter itself? You can't tell it to measure its own resistance, but you can look it up in the specifications. The internal resistance of my meter is about zero point 0.5 ohms when using the 10 amp socket. In addition, you used a couple of test leads. You might think their resistance is almost zero, but I think manufacturers have been economizing on the thickness of wire in test leads during the last 10 years or so. I put 10 leads together and measured their overall resistance as about 2 ohms. This includes resistance where the alligator clips make contact. So two test leads probably have a resistance of about zero point 0.4 ohms or more if you are using long ones. And then there are meter leads too. Because the meter, the fuse, and the leads were all in series in this experiment, you were loading the battery with a total of about 1.5 ohms, more or less. So according to Ohm's law, I equals V over R equals 9 over 1.5, which is equal to 6 amps. There's still one more factor. Even the battery itself has resistance. According to sources that I checked, a 9-volt alkaline battery has an internal resistance of about 1.5 ohms. Therefore, the battery should have delivered 3 amps. But as I said at the beginning, Ohm's law doesn't necessarily apply when you are stressing components beyond their limits. Okay, and then the last thing is cleanup and recycling. You can throw away the blown fuse. The battery may still be useful depending on how long you kept it connected with the fuse. I would store it for future use if its voltage is 8.7 volts or higher, but check it again before using it in the future experiments. In most areas, batteries can be recycled. In some areas, a law may compel compel you to recycle the batteries. Okay, so that's the experiment three. Like I said, I hope I didn't damage my multimeter by connecting things with the battery that shouldn't have been connected. The next experiment is the last one in chapter five. So maybe I'll get around to this one over the weekend. But I do have to buy some additional material. Particularly, I got to get some lemons so I can do this next experiment because the Project Trader kit doesn't come with lemons included. So I'll see you guys in the next one. Let me know what you think down below, and I'll see you guys next time.